In this section, we want to talk about units of measurement and some other things about measurements as well. Basically, the first thing we want to look at are some common things that scientists measure. And the first one here is distance or length, depending on what you're talking about. It might be called distance if you're talking about the distance from here to New York City, or it might be called length if you're measuring how long your foot is. So these are two different units. And in chemistry, we use, and in most sciences, and in most countries other than the United States, they use a metric system. And we use the metric system in chemistry. So the standard base unit of distance is the meter. 1 meter is about 39.36 inches, to give you a perspective. Or it's approximately a yard. It's a little bit more than a yard. So if you think of a football field, which is 100 yards, it's a little under 100 meters, just to give you a perspective of how long a meter is. Another unit that we commonly use is the centimeter, which is 1/100th of a meter. In this section, we will also talk about these prefixes that make metric units so useful, because a centimeter is 1/100th of a meter. A centiliter is 1/100th of a liter, a unit of volume. So they're consistent, and we'll talk about them. In the next section, we'll talk about how to convert from one unit to another. But here we have 1 inch is 2.54 centimeters. So it just gives you some perspective on distance units. Another unit we care about is mass. And a standard unit of mass is in the metric system is a gram. A gram is approximately the mass of a paperclip. Here is the National Institute of Standards and Technology, the 1 kilogram mass. So this is exactly 1 kilogram. Mass is essentially how much matter is in something. To give you a perspective with the English system, 1 gram is 0.0022 pounds, and a kilogram is about 2.2 pounds. So this gives you a little bit of perspective of the unit of mass. In chemistry, it's very common to measure mass. It's relatively uncommon to measure distance because atoms are very small, but it's very common to measure mass. Another unit we care about is temperature. Temperature has 3 scales that you can see compared to each other here. We have the Fahrenheit scale, the Celsius scale, and the Kelvin, or the absolute temperature scales. Temperature is a measure of average kinetic energy. So all the molecules, even the molecules in something solid, like the desk you might be sitting at, are moving at any temperature above absolute zero. If you were to cool these molecules down to an absolute lowest temperature, that absolute lowest temperature is the temperature at which the molecules stop moving. Now, when it comes to temperature, we do need to learn how to convert from one unit to another, and it's done slightly differently than if you wanted to convert from, say, milligrams to grams, or even if you wanted to convert from grams to pounds. These two things would be done slightly differently. So in this section, we do want to cover how you would convert from one temperature to another. And there are essentially 3 equations that you need to know in order to do this. The first is that degrees Celsius equals degrees Fahrenheit minus 32, and you do have to subtract the 32 first, divided by 1.8. You would use this one if you were given the temperature in Fahrenheit and you wanted to know the temperature in Celsius. The next equation that you need to know is that Fahrenheit equals 1.8 times degrees Celsius plus 32. And here it's the standard order of operations. You multiply first and then add. Here the order of operations are you subtract first and then you divide. That's why this is in parentheses, because that's the non-standard order of operations, if you will. And the last one is for Kelvin, the absolute temperature scale. And Kelvin is Celsius plus 273. In many books, you'll see plus 273.15, although very commonly we only measure temperature to the nearest degree, so I'm going to leave off the 0.15. If you use a typical thermometer, you usually can only get it to the nearest degree, as the degree markings are very close together. Of course, there are devices that can measure it much, much, much more accurately, so sometimes you may want to use some decimal points here, but in this course, I think this is good. So let's pick some common temperatures and let's convert them to different units. So let's take body temperature. Body temperature is a common temperature that we're all familiar with, and in the United States, we're familiar with this in Fahrenheit, which is 98.6 degrees Fahrenheit. Let's say we want to know what that temperature is in Celsius. So this could be a question on the homework, for example. So if we want to know what it is in degrees Celsius, we'd use the equation where degrees Celsius is by itself. So degrees Celsius equals the Fahrenheit degrees, 98.6, minus 32, divided by 1.8. And as I mentioned before, you need subtract first and then divide. And when you do this, you get 37 degrees Celsius. You could argue it's 37.0 degrees Celsius. We'll talk about significant figures later on, so this isn't important for right now. That's coming up in this chapter, however. Let's look at another example. Let's look at the boiling point of water. Water boils at 100 degrees Celsius. What is that in Fahrenheit, for example? So in Fahrenheit, 100 degrees Celsius, we would have to use this equation because Fahrenheit's by itself. So we take Fahrenheit equals 1.8 times 100 plus 32. And as you may know, the boiling point of water in Fahrenheit is 212 degrees Fahrenheit. So we converted from Celsius to Fahrenheit. What if we wanted that same temperature, 100 degrees Celsius, in Kelvin? Well, we could figure that out as well. Kelvin equals the 100 degrees C plus 273, which of course is 373 Kelvin. So we do need to be familiar with how to convert from one unit of temperature to another unit of temperature, and this is how these equations are how we can do this. These are a good thing to write down so that you have them handy when you need them. Another unit of measure is volume. Volume is a unit of measure that we commonly use in chemistry. And volume is a three-dimensional space. So if you take a 1 centimeter by 1 centimeter by 1 centimeter cubed, you would actually have a milliliter. And this is not 1 centimeter cubed. This, I guess, is supposed to represent the 1 centimeter cubed. But 1 centimeter cubed is defined as a milliliter. 1 decimeter cubed is defined as a liter. And then a meter cubed doesn't have a liter, it'd be multiple liters, okay, in volume. So these are some examples. Note that a centimeter cubed equaling a milliliter is something you definitely need to be familiar with. You should also note that a centimeter cube is sometimes called a cc. So, for example, if you were in a hospital setting, they might say the patient needs 5 cc's of whatever. Well, 5 cc's and 5 milliliters are the same thing. So if you have a three-dimensional space that's 1 centimeter by 1 centimeter by 1 centimeter, that is defined as a milliliter. You could also have kiloliters, you could have liters, you can have the same thing you could have with the prefixes in the other cases. And we'll talk a little bit more about the prefixes in a couple of minutes. When you have units of measurement, one thing that you have to be concerned about is sometimes you have very, very small and very, very large measurements. So let's say that you have a hair, a human hair, and the diameter is 0.0000081 meters. So this is the diameter of a hair. Or let's say that you have the distance between the uptown campus and the downtown campus at the University of Albany in millimeters, which is 61, 1, 2, 1, 2, 3 millimeters. So just counting the zeros there. So these units are very, very, in this case, a very, very small unit. And in this case, a very, very large unit is a lot of millimeters between the uptown campus and the downtown campus at UAlbany. It's vected 6.1 million millimeters. It's a very small number of meters between the university, or excuse me, for the diameter of a hair. So here we use something to express these numbers. There's actually two ways we can do this. One way we can do this is to express these numbers in scientific notation. So, scientific notation consists of two parts. Well, first I should finish writing the word. Scientific notation consists of two parts. The number out here, which is called the coefficient, which has to be between 1 to 9.9, repeating by definition. Then we have times 10, and up here we have an exponent, so a superscripted number, which is positive for large numbers, and here we define large numbers as greater than 1, and negative for small numbers, which here we define as less than 1. So these are the components. So we have an exponent, which must be between 1 to 9.9 repeating, times 10 to some exponent, which is positive for large numbers, and negative for small numbers. So let's look at our first example. Let's look at this number here. So we want to express this in scientific notation. So we need to make this 0.000081 meters into something that is between 1 and 9.9. That number means we need to put the decimal place between the 8 and the 1. So we need to get 8.1. We can't use 0.81 because that's less than 1. We can't use 81 because that's greater than 10. So we have to use 8.1. So we use 8.1. Now, the decimal place starts here. How many times do we need to move it? We need to move it 1, 2, 3, 4, 5, 6 times. So we need to move it 6 times. Times 10. So the question becomes, is it negative 6 or positive 6? Well, in this case, it is going to be a small number. This is less than 1. So it's negative 6, and the meters stays. So we have 8.1 times 10 to the minus 6 meters. Let's look at this example here. In this case, the number that we need to write is 6.1. It can't be 61. It can't be 0.61 because it has to be 1 to 9.9. So it's going to be 6.1 as the number. Well, here we don't have a decimal place. So if a number doesn't have a decimal place, we assume it's at the end. Now, how many times do we have to move it in order to make 6.1? Well, we have to move it 1, 2, 3, 4, 5, 6 times. By coincidence, they're both 6. Times 10, and then, in this case, it's a large number, right? We started with 6.1 million. That's certainly greater than 1. So it's 6.1 times 10 to the 6 millimeters. So these numbers are expressed in scientific notation. It's a very good idea to practice this a few times so that you know how to express very small and very large numbers in scientific notation. And in fact, scientific notation is useful for exactly that. This is kind of a pain to write and understand. This is much more straightforward to understand, and that's why we use scientific notations. But there are rules, and those rules are outlined here. So this is scientific notation. Another way to do this is to use different prefixes. So these are some prefixes which you may want to, refer back to in order to do the homework, for example. So some of these you've heard of, like millimeters, okay, centimeters, okay, kilo, kilometers, or kilometers. Pronounce the same thing. Some of them are used in the computer industry. Mega, which means a million. So a megabyte is a million bytes. A giga, which means a billion. So a gigabyte is a billion bytes. And tera, now these things are becoming more common. A terabyte hard drive, which is 10 to the 12 bytes. It's 1,000 times more than than a billion. So that's a tera. So that's some examples from the computer industry. You may have heard of nanotechnology. Nanotechnology is 1 times 10 to the minus 9 meters. This is in the realm of the distance between atoms. It's not quite bond distance or something like this, but it's in the realm of those sizes. So, I don't know, 50 or 100 atoms might be in the size of a nanometer if put edge to edge, depending, of course, on how big the atoms are. So, these are some different units that are used. And in the next section, we'll talk a lot about how to convert from one of these units to another. But here, I just want to give you an example of how this might relate to the previous case. So another way of expressing this 8.1 times 10 to the minus 6 meters is to call this 8.1 micrometers. And this are the same distance. So if, for example, we were measuring the width of a hair, we might want to do it in micrometers because it's more convenient, right? We get 8.1 micrometers, and then we don't have to write this in scientific notation. And this, if you recall, is the distance between UAlbany, uptown campus, and downtown campus. Okay, and this is certainly not going to be expressed in millimeters, right? If you lived in another country besides the United States and you look this up on Google Maps, for example, the distance between one part of a city and another part of a city is measured in kilometers. That's a common unit of distance. So this is 6.1 kilometers. So the reason that all of these prefixes exist is because they're convenient for different things, right? If you're measuring the distance between 2 points in a city, kilometers is a good unit. If you're measuring the width of a human hair, kilometers is not a good unit. Micrometers is a good unit. Maybe even millimeters, which was the original unit, which was bad for the distance between two cities, but even millimeters would probably be better than meters. But micrometers is probably the most appropriate. So that's why all of these different things exist. In the next section, as I mentioned, we'll talk in more detail about how to convert from, say, this number to this number, because that's an important point in chemistry. So the next thing that I want to talk a little bit about is density. So density is equal to the mass divided by the volume, or more simply, D equals m over v. This is a ratio between the mass of an object and the volume of an object, and is a common property that we use in chemistry and we measure. In fact, in the lab, if you take the lab here at UAlbany, you will actually measure the density of sugar water solutions and use it to find the amount of sugar in Coke or some other commercial soft drink. So here we have density equals mass divided by volume. So if we look here, we have a pail of water, and you can see some objects are more dense than water. So a fork, okay, which may be made out of iron, for example. Iron is more dense than water, so the fork sinks. This letter U is probably made out of some kind of foam, which is some kind of plastic polymer, a carbon polymer. And it tends to be less dense than water, so this U floats. This paintbrush is made out of several things, one of them being wood. Wood is less dense than water, so this floats. So objects layer themselves based on density. So if you look at the earth, the water tends to be on top of the soil, like in the ocean. Underneath the ocean, there's a bottom, which is soil. Soil is more dense than water, so water's on top. Air is even less dense, so the air is above the water and is above the soil. So these are just some examples of how things order themselves based on density and how they sink. As one quick example of density, I wanted to look at gold. A sample, oops, I need to put this on the screen. A sample of gold has a mass of 50 grams and a volume of 2.59 milliliters. What is the density? All right, so we want to find the density of the gold. And it turns out that gold is one of the most dense substances that there is. So, if you recall from the previous slide, density equals mass divided by volume. Typically, the mass is in grams, and typically the volume is in milliliters or centimeters cubed. Note that a milliliter and a centimeter cubed, or a cc, are the exact same thing. As I mentioned before, if you have a cube that's 1 centimeter by 1 centimeter by, it's hard to see here, but this back 1 centimeter, then this holds 1 milliliter of volume. So 1 centimeter cube is a milliliter. So sometimes your units are in milliliters, sometimes they're in centimeters cubed. Some books will say this is for liquids and this is for solids, but I've seen both used interchangeably. So back to the original problem. We're given a mass and we're given a volume. So density equals the mass, 50.0 grams, divided by the volume, 2.59 milliliters. So in this case, we get 19.3 grams per milliliter. So gold has a density of 19.3 grams per milliliter. And this is constant. It doesn't matter at a certain temperature. It doesn't matter where the sample of gold comes from. It doesn't matter if the sample of gold is from the United States or from China or wherever. It doesn't matter. Gold has a density of 19.3 grams per milliliter. And this is one of the most dense substances on Earth. And in fact, density was invented when people were trying to figure out whether crowns or other things that were supposed to be made out of gold actually were made out of gold. And one way to identify gold is through its incredibly high density. If you use a different metal, such as silver, has a much lower density, and that makes it distinguishable from gold. So if you measure the mass of the object and you measure the volume of the object, if it's made out of gold, the ratio of the mass and the volume will be 19.3 grams per milliliter. Density is a good thing to calculate because it kind of ties together several of the concepts we're going to learn in this chapter. So in later videos in this chapter, we will talk a little bit more about how we could actually calculate the density of the object and take into account things like significant figures and making accurate measurements and things like this. The last thing that I want to mention in this section is the difference between intensive and extensive properties. So intensive properties are properties that are independent of the amount of the material. So it doesn't matter how much material we have. And we just mentioned density is an intensive property. It doesn't matter where the gold comes from. Its mass to volume ratio is constant. If we look at water here, so say this is a bathtub full of water, and this is a cup of water that came from this bathtub, the density of this water in the cup is 1 gram per milliliter. The density of this water in the bathtub is still 1 gram per milliliter. There's a lot more milliliters, but there's also a lot more grams. There's a lot less milliliters here, but there's also a lot less mass. So the densities are constant. Temperature is another intensive property that's independent of the amount of the material. If this water is at 20 degrees Celsius, and it came from this bathtub, which is also at 20 degrees Celsius, that would be a cold bath. That's room temperature. A bathtub would probably be closer to 38 or 39 degrees Celsius. Okay, but in this case, these things would have the same temperature. So it doesn't matter if the sample is in the bathtub or the sample is in the cup, they have the same temperature. So that's an intensive property. Extensive properties depend on the amount of the material. The mass of water in this cup is far less than the mass of the water in this bathtub. The volume of water in this cup is far less than the volume of the water in this bathtub. So these are extensive properties because they depend on how much you have. Less water means less mass and less volume. More water means more mass and more volume. So those are extensive properties. The final thing I want to mention as we conclude the video, if you notice, whenever we make a measurement, we put a unit at the end. And in the lab, as well as in the course, having units is super important. If you see something like milliliters written after a number, you know that somebody was measuring volume. If you see grams, you know they were measuring mass. If you see degrees Celsius, you know they were measuring temperature. So putting units, even though it can be seen of as busy work or a pain in the butt, is super important in science because it allows everyone else to know what you measured. We can't simply assume other people know what we're trying to measure. That's where units come into play.